So in this video, we are going to continue with some extra stuff for the decision tree algorithm. In the previous video, we implemented the construction, the tree construction part, but now we're going to implement the classification part, which means like how to actually we use the tree when we get new data and we want to predict the label for that data. So one thing that is missing from the previous implementation is that even though we are printing the value of every node and the value of the parent to keep track of the path we are following, for the classification part, we are going to use those values to see from which branch to move a given new data point, right? But extracting this value from the string that we are printing here is kind of complicated. So this is why we're going to just add a couple of fields to the current tree in order to extract the value later. So treelib allows us to do this in a very easy way. We just need to create an extension, let's say an extension of the tree, of a tree node. Let's say we're gonna call it my node, and we are going to just, we're gonna create a class that has the extra fields that we wanna add to our nodes. We are going to need the value and the value of the parent. We just initialize this in the usual way we do this with classes. Now, every time we create a node, like here, for example, we are just going to store the value of these fields. In treelib, we just need to use an argument called data, and here we just add the information we just declared in our previous class. So it's going to be my node, and we are going to pass the value on the parent value. So the value of the node is this one, right? And the parent value is this one. Okay, something similar we are going to do in the next part where we create a node, which is here. In this case is the prediction, the value of the node. And the last test is when we create a node for the winner, right? So again, here, so here's winner. Winner is already a string. And in this case, it's also winner. Recall that here basically we are printing the same thing. It's just when it's a root, we don't want to print empty values of the parent. So this is why we do this, right? We just, it's exactly the same set of arguments, but in this case, we are printing just the name of the node. So now, as I said, now we are passing new parameters that are going to be used in the classification part. Okay. So let's run this and this. Okay, so now we need to implement our classification function that is going to be called, let's say, classify tree. and it's going to receive a tree and a new data point. Let's call it X. Okay. So we're going to set like a if we're going to extract the root of this node. Given that it is a recursive function, every time we get the tree, we may be getting an internal node as a tree, right? So when we call the tree.root, we are accessing the ID of the root node of the current subtree. So when we index tree in this ID, we obtain the root node of the current tree. And we ask if it is a leaf node. So when it's true, we are going to return actually I'm going to copy this, that data.value. So here we are predicting the value of the leaf node. And when it's not a leaf, we are going to do the recursive call. So here we obtain the ID of the node. Let's do this here better. That's better. Okay. So we are going to iterate in the branches of the node. All these functions is branches provided by the tree library. So we are going, H is each of the branches of the node NID. Here we are basically validating if X should go down through the H branch or not, right? So we need to calculate the value of, sorry, forgot to mention that I'm assuming that here X is a pandas data frame row. It's an entry, one entry, okay? So this is going to return the value of X in the variable corresponding to this branch. Right, because this is the value of the node we are assessing. So if we call X of that name of the node, we are getting the actual value. And we are going to compare it with the tree, with this branch, okay? And we are going to see if the parent of this branch is matching with the current value of X. That, right? Because again, let's say, for example, if the node is weather, so we are checking the value of X in the variable weather, and then when we compare one of the childs, remember that each child has the value of the parent because we went down from the parent to the child thanks to the value of the parent. So we compare that variable with the value of the parent of the current branch. So again, what we are doing here is like we are first getting the value of the branch. Let's say, for example, weather. So then we are getting the value of weather in the new data point. And we see, let's say it's sunny. So if we obtain sunny, then we need to see what was the value of the parent when we come to the current node, right? Because the parent basically send us to this node because we instantiate the value of the parent in that part. So this is why we obtain here for the current branch, the parent node is actually the parent value. So if that happens, means that we need to go down in that direction. So we are going to return the same function. We are calling the subtree of this ID, which is H, right? And we are going to send as the new version of X the same data, but we need to drop the variable that we already instantiate. So in this case is the tree is this variable, right? an in pandas drop, we need to provide with the access of the dropping. In this case, we are dropping a column, so it is 1. I believe that's it. So now, for example, let's create a new data entry. Okay, so let's assume we want to classify that entry. So let's say that the label or the prediction is going to be classify tree of t, that is the current tree we have, and this data point x. Let's print the label, and the label is movies. Makes sense, right? Because if it's sunny, yes, and good, if we go to our tree, so if it's with parentheses, yes, so it's this branch, the weather is sunny is this branch, and the economical situation is good is this branch, we get movies, right? So the classification is working. Cool. So we can improve this by adding some prints if you want to follow the path that the data point is traveling since it enters from the root to the leaf. Also, it's important to add some assessments, in the sense like we need to make sure that the variables that are described in the data we want to classify are the same variables that the tree has in the nodes. Okay, so you need to add some exception handling in this part. Something else we can do to improve our implementation is by adding this option of binarize the continuous data. So I left the space here to add these functions. So because currently our model only works with discrete data, so let's say that we get continuous variables, how we could handle them to use the same decision tree construction algorithm we have implemented so far. So recall that from the previous video and slides, we showed some techniques to binarize continuous data. So let's implement one of them. So we are going to need the binarize function for one specific variable. Let's say in this case, we know the split point. Okay, later we're going to implement the other functions. The number of data points is going to be the size of the var. The new data, or the binarized data, is we are going to initialize in a copy of the var, and then we are going to iterate So here we just check if the variable, if that row the new data is going to be let's say that's going to be one value. So we're going to define this A and B. So let's say that A we want these nodes to keep the information of the split point in the tree. So let's call them like here we go. So now every time when we see a binarized node in the tree, it's going to tell us where is cutting in order to decide if we go from one side or from the other side below the node. Okay, but this function is receiving the variable and the split point. We also need to know how to find the split point. For a given variable, but we're gonna need the labels. Let's use this option where we randomly choose a given set of points from the current data points and try them and pick the best one. Here we're getting a sample of 30% of the points, and our candidates we're going to choose n candidates, and we don't want to repeat them, right? This is why we put replace equal false. Okay, so now we use the usual thing to obtain the maximum. So here we use the previous function. And we try all the split points, all the candidates, right? It means that we calculate the information gain of each of these candidate splits, and we're gonna choose the maximum. And that's it. So here we are selecting a sample of candidates split points, and then we try each of them and we select the one with highest information gain. So we're almost there. So now we need to build a function that binarizes all the variables. So here we are selecting just the list of variables. We want to discard the class. Now we create the new data. Here we use our previous function of the new data indexed in the var, and we need to pass the class, right? So there we found the split. Now we need to binarize that variable. With that specific split point, and then we just replace this variable with the binarized one, and we just return the new data. Cool. So let's test the binarization. So let's use some continuous data that we can get from any of the libraries. Let's use the famous Iris database. Let's create a data frame. Now we just add the class column. Let's call it class. They call it target in the load iris functions. Okay, here we go. Now let's try our binarization functions. We have some problem in this part. Yes, this. Let's print a sample of this. Let's visualize 30% of the Binarize database. Here we go. So these are the new values of the variables, right? Now we can try actually our decision tree with this new database. So here we can pass data bin. The class name is class. And there we go. So here we have a decision tree for the Iris database according to our binarization process. Cool, so you can still keep adding new features for the code. For example, you should add the minimum amount of rows before creating the split. That is very simple because here we just need to add a new stopping criterion that counts the amount of remaining rows, and if it is smaller than a given number, then we just return the leaf with the most frequent class. And that's it. And in that case, we're going to have a decision tree that is more robust to overfitting.